Welcome to Math Methods, Lecture 17, Introduction to Green's Functions. To get started, consider a general second-order linear inhomogeneous ordinary differential equation, such as the one in equation 17.1. The point of a Green's function is that we can write down a specific solution to this inhomogeneous ordinary differential equation in equation 17.2. So that y of x is given as an integral over the Green's function g times the right-hand side of the inhomogeneous differential equation. The aim of the lecture is to prove this relation 17.2 and give ways to obtain the Green's function g. First, let's write the inhomogeneous ordinary differential equation in the form differential operator Lx acting on y is equal to b, where the differential operator Lx is defined as follows in equation 17.4. So minus second derivative plus arbitrary coefficient function a1 of x, first derivative, plus a0 of x. We can then define a Green's function g of x and y such that the derivative operator acting on g is equal to the Dirac delta function delta of x minus y. Once we have this definition, we can actually prove that the equation 17.2 is a specific solution to the inhomogeneous differential equation 17.1. To do that, act with the differential operator on the specific solution 17.2. So Lx acting on y of x is equal to Lx acting on the integral over dy g of x and y times b of y. And I apologize for the slightly confusing notation that I use the function y of x as a function, but have also used the symbol y to denote the coordinate y that I use in my Green's function. So these are not the same y, which is slightly confusing. The integral on the right-hand side is over y, and that means that the operator Lx can be pulled inside the integral. Doing that, the differential operator will act on the Green's function g, and we get the delta function as in the definition 17.5. Once we have that, the integral over y and the delta function just reproduces the function b of argument x that we need on the right-hand side of the inhomogeneous differential equation. We have sort of shown that the Green's function can be used to obtain a specific solution to the inhomogeneous differential equation, but we can also obtain a general solution to that inhomogeneous differential equation. To do that, we also need two linearly independent solutions, y1 of x and y2 of x, such that Lx acting on y1 or 2 is equal to 0. That's the homogeneous ordinary differential equation. They have to be linearly independent, and one way to check that is that through the Wronskian defined in lecture 4 being non-vanishing for these two solutions, y1 and y2. The general solution to the differential equation is then given as the integral over the Green's function and the linear combination of the functions y1 and y2, which constitute the homogeneous solution. We can also write a specific solution with specific boundary conditions for the function y of x by imposing the boundary conditions on the Green's function g of x and y. So if we have such a Green's function that obeys the specific boundary condition, then the specific solution y of x is just an integral over this specific Green's function with these particular boundary conditions. Now that we know how to sort of use the Green's function once we have it, let me now discuss different methods on constructing the Green's function for a given operator Lx. Depending on the operator Lx, there are different methods to construct the Green's function, and these methods will differ in their sort of easiness of applicability. And sometimes it may also be the case that there's no known method that actually gives an easy way to construct the Green's function. In the following, I will discuss two methods to obtain g of x and y for two slightly different types of differential operators. So let me get started with the first method, which is based on knowing the solutions to a homogeneous ordinary differential equation. So assuming that we know two linearly independent solutions, y1 of x and y2 of x, to the homogeneous ordinary differential equation, Lx on y0, we can construct the Green's function as follows. G of x and y is given as a step function x minus y of the linear combination y1 of x, y2 of y, times a coefficient function c1 of y, and then a step function y minus x with the different combination of solutions y1 of y, y2 of x, with a different coefficient function c2 of y. So this is an ansatz for this Green's function with theta the step function, and in the following we will sort of show in particular what we have to choose for these coefficients functions such that g is the correct Green's function in the definition that we sort of used before. So to do this, let's act on this ansatz with the differential operator Lx, which is given as minus the second derivative of the Green's function plus coefficient function a1 of x first derivative plus a0 on g. So we know that we'll need first order derivatives at least for the Green's function, and we can do a first order derivative of equation 17.11. And what we find is that there will be terms where the differential operator acts on the step function, producing a Dirac delta function. So for instance, there will be one Dirac delta function over here, and there will also be a Dirac delta function for the second term, but with a minus sign because of the chain rule. So then we get a term in the first derivative of the Green's function that is proportional to c1 minus c2 and the delta function, and the two y's where the argument of the y's doesn't play any role because the delta function restricts x and y to be the same anyways. Now that is one part of the differential operator acting on g, where it hits the step functions, but in addition there will be other terms where, for instance, the differential operator acts on y1 of x in the first term, that gives us this term over here, and when the differential operator acts on y2 of x, which gives us the term over there. Now this is the first order differential operator on g, but in the definition of L of x on g, we have minus two derivative of x acting on g. So we will get, in general, another one where we have a differential acting on delta of x that results in a delta prime. We don't want any delta primes because in the definition of the Green's function, there's only a delta on the right-hand side, but no delta prime. So there's an easy way that we can forbid this, which is that this coefficient that is proportional to delta in the first derivative of g has to have coefficient 0, which just means that the coefficient functions c1 and c2 have to be equal. So if you do this, then the first order derivative only has these other terms that were in the last line of the equation on the last slide. And we can take another derivative of this to produce the following form. So we have something where we now have the second derivative act again on the delta functions. We get a delta function, and the argument is proportional to c1 and y prime, y2 minus y1, y2 prime. And then we have the second order differential acting on y1 and once on y2. So we can see that we can get the delta function with the right coefficient from this first term here if this coefficient function c1 is just minus, because of the definition of the minus d by dx squared term for the delta function, times this combination here, which can be recognized to be nothing else but the Wronskian of the two solutions y1 and y2. So if we choose c1 to be this particular Wronskian, then we'll get the right coefficient of the delta function on the right-hand side. We'll get some other terms as well. So if we collect everything together, we have that the differential operator acting on g produces the delta function. That was what we engineered. And then we have other terms where the differential operator acts on y1, and another term where the differential operator acts on y2. but we assumed that y1 and y2 are two solutions to the homogeneous differential equation, so that Lx acting on y1 or y2 is equal to 0. So both of these terms vanish, and we get that Lx of g is just delta of x minus y, which is what we wanted to prove. To summarize, we have an explicit way of constructing the Green's function g for the operator Lx, given the two homogeneous or two linearly independent solutions of the differential equation Lxy is equal to 0. And the equation 17.19 is this explicit form of constructing the Green's function. And of course, we need to know these two independent solutions, y1 and y2, and they sort of have to have non-vanishing Wronskian. Otherwise, this Green's function here is nonsensical. Okay, for the second method, we sort of take a slightly different approach. Let me in particular consider the Schrödinger equation as an example for a differential equation. So Schrödinger equation is given in equation 17.21 with V of x the potential and E the eigenenergy. This equation is not an inhomogeneous differential equation, but we can pretend it was by simply calling this right-hand side B of x, with B of x being 2me psi of x. Then this first piece here is just the differential operator. It is given as minus d squared by dx squared plus 2mv of x. And using our construction for the Green's function, we can write down a formal solution to this equation as psi of x is equal to 2me integral over the Green's function and psi of y. So it's an implicit solution to the wave function psi of x. And it may seem that we have not gained very much in this construction because psi appears both on the left-hand and right-hand side of this equation. But it turns out that this form is useful and it contains information that is difficult to extract otherwise. To see this, first note that the eigenfunctions to Schrödinger's equation form a complete set of basis states. In particular, the psi n's are the eigenvectors of the differential equation, and the E-n's are the corresponding eigenvalues of the differential equation. The psi n's are complete, so that means that the sum over psi n of x, psi n of y, summed over all n, just reproduces the Dirac delta function x minus y. Since the psi n's are complete, we can expand g of x of y in terms of this size. And because g of x and y must be symmetric, we find that we have to have the following expansion: g of x and y as a sum over all n, with this combination psi of n of x, psi of n of y, with unknown coefficients cn. We can fix these coefficients cn as follows. If we plug in the definition of the Green's function, we know that the differential operator acting on g has to be equal to the delta function. But the expansion of g in terms of this sum means that the differential operator acts on psi n of x. So the delta function is something we get if we just use the completeness of the wave functions psi n. And the Lx on a psi n, we know that we can get from the definition of the wave function psi n and eigenvalues En. So the right-hand side here becomes a sum over all n times 2m En Cn psi n of x, psi n of y, and that has to be equal to the combination psi n of x, psi n of y on the right-hand side. In order for this to be true, these coefficient functions or coefficients Cn have to have a particular value. They need to be 1 over 2m En. So that we find that after this exercise, there's a second way to construct the Green's function. And it's simply given that the Green's function is a sum over the eigen functions of the differential operator of the homogeneous system. So Lx psi n is equal to lambda n psi n divided by the corresponding eigenvalues. For our example, the wave functions were real, so psi n dagger of x was equal to psi of x, but in general, the form 17.29 is the appropriate one when the wave functions can be complex. So now that we have these two different methods to obtaining the Green's function, we can use a combination of these two to get some interesting results. The application I want to consider in the following is that of the triangle potential V of x is equal to the absolute value of x. So in this case, we know that there are sort of two sectors. There's the parity even sector and the parity odd sector. The parity even sector corresponds to the even energy levels En, so E0, E2, E4, and so on. And the parity odd sector corresponds to the odd energy levels, E1, E3, E5, and so on. Turns out that the eigenfunctions in both of these parity sectors are complete, so we can use this decomposition we had before separately in the parity even sector, which I denote with a plus, and the parity odd sector, which I denote as a minus. So for the parity even sector, we now have the sum over all the even wave functions and the even eigenvalues. And because the wave functions are normalized, we also find that g plus of xx involves psi n dagger of x, psi n of x. And if we integrate over x, we use the fact that the wave functions are normalized to find that this integral here just gives us a 1 in the numerator. And this integral over this Green's function, therefore, is the sum over 1 over 2m times the eigenvalues, and that is nothing else but 1 over 2m times the spectral zeta function in the parity even sector, so the plus here of argument 1, because the eigenvalues are taken to the power 1. This not only works for this particular spectral zeta function that I had in this example here, but works for other spectral zeta functions as well. For instance, if we take the product of two of these Green's functions with the following arguments, x, y, and yx, and we integrate over both x and y, we find that again we can use the normalization of the wave functions to show that this combination gives us the sum over 1 over 2m e2n squared, which is the same as 1 over 2m squared times the spectral zeta function of argument 2 in the parity even subsector. So if we know the Green's function, we directly get values for the spectral zeta function out of this construction. So for the triangle potential, we know how to construct the Green's function. If we choose units where 2m is equal to 1 for simplicity, the homogeneous problem is simply given by the differential equation in 17.34, which you can recognize to be nothing else but the Airy function differential equation that we discussed in an earlier lecture. So the solutions to this homogeneous problem are the Airy functions ai and bi. And if we wanted to restrict on the parity even subsector, we have to impose the boundary condition that the solution vanishes at infinity and that its first derivative at 0 is equal to 0. We can then find that there's a particular combination of the functions ai and bi that fulfills these two conditions. For instance, the function y1 of x equal to ai, that one has the property that it decreases exponentially for large x, which will give us the behavior that the Green's function at infinity is equal to 0, according to the boundary conditions. And if you sort of take the following linear combinations between ai and bi for y2, this particular combination y2 has the property that it has 0 derivative at the origin, which is necessary for the parity even subsector that we want to consider. The Wronskian between these two solutions is also known as just minus 1 over square root of 3 times pi. And then we can write down the Green's function explicitly using our method 1 in this following form, where you can check that this first term where x always has to be bigger than y, that is the one that has y1 of x over here. So if x is very, very big, y1 of x takes this role here, and that is the function that sort of decreases exponentially. Whereas in this term over here, that's the one where x has to be smaller than y, in particular close to 0. That's the one where y2 of x will be the function that determines the behavior close to the origin, and that's the function that has zero derivative at the origin, which is necessary for the parity even subsector. So once we have the Green's function, we can use this to immediately calculate the spectral zeta function psi s of argument 2 in the parity even subsector. Again, choosing units where 2m is equal to 1. The spectral zeta function is just given as this double integral of the product of these two Green's function. If we use the step function, this turns into the following double integral, which has the y1 squared and the y2 squareds and the corresponding opposite combination over here. And the integrals over the Airy functions are analytically known, so we find that we can do all of these integrals and get for zeta as plus of 2 the following form: 6 pi 3 to the power of 1/6 divided by gamma squared of argument minus 1/3, or numerically about 1.37. Before summarizing, let me quickly point out that this was an example where we calculated zeta as plus of 2, but we can do a similar construction for other zeta functions. In particular, we can do a construction for the Green's function in the parity odd subsector, and we will correspondingly get the zeta function in the parity odd subsector. We could also just add them up and get the zeta function outright, so not in any subsector, but just summed up. Or we can do similar constructions for the zeta functions for other potentials. To summarize, in this lecture I discussed the use of Green's functions. We learned that knowledge of the Green's functions can be used to obtain the solutions for the inhomogeneous ordinary differential equations. We learned two particular methods to construct Green's functions based on knowledge of the solutions to the homogeneous problem. We established a relation between the Green's functions and the spectral zeta function and used this in an application to calculate the spectral zeta function for the triangle potential. That's it for today.